Work. What is work? Work is the amount of energy required to perform a physical task. Work is done when a force that is applied to an object moves that object. Let's take a closer look at force. Force can be thought of as the pushing or pulling of an object. Force is calculated by the equation force equals mass times acceleration. And let's recall that acceleration is the second derivative of position. Acceleration is typically gravity, and gravity is represented as 9.8 meters per second squared, or 32 feet per second squared. So the units of force are commonly either newtons, where newtons is kilograms, that's our mass, times meters per second squared, our acceleration in terms of gravity, or a unit of pounds. So in this lesson on work, for some problems only mass is provided, so we would need to multiply by gravity, and sometimes weight, a force that already includes gravity, is provided. Let's start by talking about work with a constant force. When force is constant, work is calculated by multiplying the force by the amount of movement of an object. So the equation looks like W equals F times D, or work is equal to the constant force times the distance the object moves. This might be another helpful way to remember this formula. We said force is equal to mass times acceleration. So this formula becomes W equals M times A, mass times acceleration, times the distance the object travels, or work makes me mad. The units of work are commonly Newton meter, which is called a joule, or foot-pound. Let's look at an example. If you push an automobile 20 feet along a level road while exerting a constant force of 90 pounds, how much work have you done? Since the force is constant, we can use the formula work, W, is equal to force times distance traveled. The force was 90 pounds times the distance traveled was 20 feet. So this ends up becoming 90 times 20, or 1,800 foot-pounds. Let's take a second to think about this graphically. If we go ahead and put distance in feet on the horizontal axis and force in pounds on the vertical axis, our graph will be just a horizontal line at 90 because we have a constant force. So here on the x-axis, our distance extends from 0 to 20. Finding work was multiplying force times distance, so that was essentially finding the area between 0 and 20 underneath the force function. Now let's talk about work with varying force. When the force varies, as opposed to staying constant, we must integrate to find work. The work formula becomes W equals the integral from x equals a to x equals b of the force function f of x dx. Note here, x represents an object's position. So we are integrating over the distance traveled, so that's finding the area underneath the force function over the distance traveled. Our next example is going to be asking us to find the work done in stretching a spring a certain distance. So in general, a spring lies at some natural length, and then a force is required to either stretch or compress that spring. So let's go ahead and take a look at Hooke's law for springs. the force that is required to hold a stretched or compressed spring, x units from its natural length, is given by the following equation. Force is equal to k times x, where k is called the force constant or the spring constant. And the units of that k value is newtons per meter or pounds per foot. So here we have force that is not constant. Force is linear with a slope of some k. Let's look at an example. A force of 9 pounds is required to stretch a spring from its natural length of 6 feet to a length of 8 feet. Find the work done in stretching the spring, A, from its natural length to a length of 10 feet, and B, from a length of 7 feet to a length of 9 feet. So here, to find the work, we know that we need to integrate the force function. And when we have a spring involved, we know that the force function we should be thinking about is from Hooke's law. Force is equal to the spring constant times x, where x is the amount that the spring is either stretched or compressed from its natural length. So let's go ahead and start to set up what we can of our integral needed to find the work for part A. So for part A, to find the work, we're going to need to set up the integral from x equals, all right, so since in part A, we want the work done in stretching the spring from its natural length, that means that the distance traveled there is x equals 0. So the natural length, no work has been done, it's just resting there. So we're starting at x equals 0, and then we're stretching to a length of 10 feet. But the natural length was, of course, 6 feet. And so if that corresponds to x equals 0, then stretching to a length of 10 feet means that our upper limit of integration is x equals 4. So our integral starts at 0, goes up to 4, and we're integrating the force function k times x. But what we're missing here is the value of k. We're missing the spring constant. This needs to be a numerical value. And we aren't given this value explicitly here. We have to solve for it. We do have enough information to find it though. We are told that a force of 9 pounds is required to stretch a spring from its natural length of 6 to a length of 8 feet. So to stretch the spring 2 feet, that's the distance traveled by the spring, that takes 9 pounds. So we're going to use this equation here to solve for the value of k. So I'm going to go ahead and write down here, if we know that force is equal to the spring constant times k, well, the force of 9 pounds is equal to k times a distance of 2 feet. That's how much the string is being stretched from its natural length of 6 feet to a length of 8 feet. So I can go ahead and solve for k here. So if I divide by 2 feet, I have k is equal to 9/2 pounds per foot. And so notice that I'm keeping my units with me just because I want to go ahead and do sort of a units check on this problem eventually. So I'm going to take this value of k over here for a second into the integral now. So we are integrating from 0 to 4 of 9/2, and the units was pounds per foot on that spring constant, and then times x. Well, x is corresponding to that distance. So the units of x would be in feet. And then we have dx. So the units that are canceling here are feet. So what we're integrating is 9/2 x pounds, which should make sense because this represents a force. K times x is a force, and force is measured in either pounds or in newtons. So what we have here in terms of the force function, the units there make sense. And the units on the limits of integration are in feet. Those are distance. From 0 feet, we're stretching it out a total of 4 feet to get to this length of 10 from 6. So the units here check out. I just wanted to do that to sort of get started here. But now to integrate, I'm going to go ahead and remove the units just to make it look a little cleaner. We're integrating just 9/2 x dx. So I'm going to go ahead and bring that work over here, and that's going to be the fundamental theorem of calculus. So I'm going to leave the 9/2, and we're going to take the antiderivative of x, that's x squared over 2, evaluated from 0 to 4. So that's 9/4, and then we'd plug in 4 and square it. 9/4 times 4 squared minus, and then we plug in 0, although that's going to just be 0 for that term. So now here, what we end up with is just 9 times 4 after one of these 4's cancels, which is 36. And so the units here on work are going to be foot-pounds. So our options are joules, which are Newton meters, or foot-pounds. And this problem was set up perfectly because it had feet as the distance and pounds as the force. So we have 36 foot-pounds as our answer to part A. Let's also just go ahead and make sure that the area concept is there, or the idea of area under this curve. So what we did was evaluate this definite integral of a linear function, 9/2 x, that passes through the origin. So 9/2 x passes through the origin. The units, again, were pounds for the force, and then for the distance, the units were in feet. And so we integrated from 0 to 4. Well, integrating underneath this linear function is finding this area here, technically of this little triangle. But the area is that base times height idea, right? So 1/2 base times height. Well, the units of the base are feet, and the unit of the height, the force, is pounds, and that's how we're ending up with foot-pounds. So that the units of the base, feet, and then times the unit of the height, pounds. Foot times pounds gives us foot-pounds. Now on to part B. The good news is that we're talking about the same spring in part B, and so the force function that we are still going to use is 9/2, the spring constant from before, times x. The only thing that's going to change is the limits of integration. Now we want to find the work done in stretching the spring from a length of 7 feet to a length of 9 feet. Well, the natural length, again, was 6 feet, which corresponded to x equals 0, and 10 feet then corresponded to x equals 4, so 4 feet away from that natural length of 6 feet. So for part B, a length of 7 feet is going to correspond to x being 1 foot away from the natural length at 7 feet, and at 9 feet, that's x equals 3 feet away from the natural length of 6 feet. So to find the work in part B, we're going to set up the integral from 1 to 3 of 9/2 x dx. And we already know our simplified antiderivative was 9/4 x squared. And we're going to go ahead and substitute in 1 and 3. So we're going to plug 3 in first. We're going to end up with 9/4 times 3 squared minus 9/4 times 1 squared. And that's going to go ahead and give us 9 times 9 is 81. So 81 over 4 minus 9 over 4. That's 72 over 4, which is a nice even number. It is 18. And the units are still foot-pounds. And if we take a brief second to think about the reasonableness of our answers, the answer to part A was 36 foot-pounds. So it should make sense that it would be more energy, more work to find or to stretch from a natural length to 10 feet, a total distance of 4, versus stretching from 7 feet to 9 feet, is a lesser amount of work. Let's look at another spring example. How much work is needed to stretch a spring from 0.2 kilometers to 0.3 kilometers from its natural length if 4 joules of work is needed to stretch the spring 0.1 kilometers from its natural length? All right, so on this problem, we have a couple of different things we need to think about. This time, the units involved are joules and kilometers. So we know that joules is a measure of work, and it corresponds to Newton meters. So the red flag here is that the distances are given in kilometers. So we are going to need to do a unit conversion. To get from kilometers to meters, we're going to have to multiply by 1,000. And so we're going to need to move that decimal over 3 places to the right, so that 0.2 kilometers is going to end up being 200 meters, and 0.3 kilometers is 300 meters. And the other value that is in kilometers is this distance here, 0.1 kilometers, which would then be 100 meters. So that's the first thing I would do to start with, turn everything into meters so that we're going to have the correct units. So in that previous problem, we already had foot and pounds, but let's say we had inches provided. To start the problem, we would convert those inches into feet to start with. Okay. So how much work is needed to stretch a spring from 0.2 kilometers to 0.3 kilometers from its natural length? All right, so we're going to start by setting up the integral. So the work is the integral from 200 meters to 300 meters. So we want to stretch the spring from 200 meters to 300 meters from its natural length. So we're given the limits of integration there. But just like last time, we are not given the spring constant. So we are not given the value of k. So we're going to have the force is k times x, but we're not given the value of k. And this one's also different than the last problem because we are given some more information, but we're not given the force. This time we're actually given the amount of work. So if 4 joules of work is needed to stretch the spring 0.1 kilometers from its natural length. So we're still going to need to solve a little equation on the side, but it is not F equals kx. So I'm about to cross that out right now because we're not going to replace this left-hand side, F, by 4 joules because joules is not a measurement of force. Our measurements of force are pounds or Newton meters. So we're not going to use this equation. We know that work is equal to an integral. Right? So the integral from x equals, now here's what we know. 4 joules of work is needed to stretch the spring 100 meters from its natural length. So its natural length would mean x equals 0 to x equals 100 of k times x dx. So again, we are searching for this value of k, and we can substitute in something for work here. We know that work is 4 joules. So I can go ahead and replace W with 4 and solve this for K. So we're going to have the antiderivative of K times X is kx squared over 2, evaluated from 0 to 100. That has to equal 4. And then if I plug in 100 and 0, well, 0 is going to make that term disappear. So just plugging in 100, I'm going to get k times 100 squared over 2 is equal to 4. And so if I multiply by 2, I'm going to end up with 8. So 8 is equal to k times 100 squared, and then I would divide by that 100. So let's see. I'm going to make some room up here. So I have 8 over 100 squared, divide by 100 squared. So 8 over 100 squared is going to be a decimal 0.0008. That is my spring constant, my value of k. So I'm going to take that value back over here to this integral. So we're integrating 200 to 300 of 0.0008 x dx. And then the antiderivative is going to end up being this 0.0008 x squared over 2, evaluated from 200 to 300. We're going to plug in the 300 first, 0.0004. Let's go ahead and do that because we're dividing by 2 here. X squared, so that's 300 squared minus 0.0004 times 200 squared. And I will just tell you that value actually works out to be very nice. It's 20. It is 20. And the units that are going to come out of this is going to be joules. And again, that should make sense that these limits of integration, 200 and 300, are meters. And then the force function right here is in newtons. So the force function ends up in newtons, and so we're going to have Newton meters. But Newton's meters are called joules. So you have the choice. You can either put Newton meters or joules. Let's take a look at another work example. This time we're talking about a rope. A heavy rope 50 feet long weighs 2 pounds per foot and hangs over the edge of a building 120 feet high. Part A. How much work is required to pull the rope to the top? Let's start by drawing a diagram. So here, this rectangle represents the building with a height of 120 feet. And here we have a 50-foot long rope hanging off the top. Initially, this rope weighs a total of 100 pounds because we are told that the rope weighs 2 pounds per foot. And so if it's 50 feet long and 2 pounds per foot, we have 100 pounds worth of rope hanging off the side. And so we want to compute how much work is done or required to pull the rope to the top. So we're pulling an object, there's that force, and the force is not constant, the force is changing because each time we sort of think about yanking a piece of the rope onto the top of the building, the rope is getting lighter. So kind of each foot, imagine that we're pulling onto the top of the building, the remaining part of that rope is now dropping in weight, right, in pounds. So that force is varying over time. So now what we have to do is think about how to set this up as an integral. What's the distance that's being traveled here? And then what is exactly that equation for this varying force? All right, so what I want to do is sort of think about this on an XY plane initially. So I'm going to think about the building's height as like the y-axis, and then the floor as the x-axis. And so the rope sort of initially dangling there from that height of 120 feet and it being 50 foot long, that means that the y value, where the bottom of the rope is dangling, would be at a height of 70 feet high. So I'm going to say that's y equals 70 feet high. And then again, the top of the building is that 120 feet. So the limits of integration that I'm going to go ahead and set up here to calculate my work are going to extend from 70 to 120. So those are going to be my limits of integration. They are measured in feet. They are a distance. And that's, again, where the rope initially lies. So now let's go ahead and think about what this force function is going to be. So this is going to have to be a function of y, because I made my limits of integration y values. Again, I thought about this as the x-axis and the y-axis. So I have to think about, what is this force function going to be? Well, again, it's dependent upon the weight of each foot of rope. So here we're going to have that 2 pounds per foot included. So I'm going to put 2 pounds per foot, right? But it's the force is going to decrease over time depending on how much rope is left over. So to represent how much rope is left over, that distance, well, let's just kind of pick an arbitrary y value in between 70 and 120 to kind of help us think about this. So let's go ahead and just kind of pick some y value between 70 and 120. So let's say, for example, y is equal to 80. So at the exact moment when y is equal to 80, that means that 10 feet of rope has already been lifted. So if we're starting at a y value of 70, if I'm now thinking about y is equal to 80, that means 10 feet of the rope has already been lifted. So now there's 40 feet of rope remaining. And so 40 times 2 pounds per foot would mean that I have 80 pounds of force that is being exerted at that moment of time when we're talking about y equals 80. So what we want to go ahead and set up here is a difference. So we said that the distance was 40 feet when y is equal to 80, because 10 feet had already been lifted up if y is equal to 80. So if I want to get 40 out, that means that the distance that I have to consider inside the parentheses here is going to have to be 120 minus y. And again, that's going to be in feet. So again, let's just plug in a number and sort of think about this. Let's actually start by plugging in 70. So if I think about plugging in 70, then 120 minus 70 is 50. And so that's when the entire rope is hanging there. And 50 feet times 2 pounds per feet would give me 100 pounds. So the force there is 100 pounds. And then again, we already checked what happens if, let's say, y was equal to 80. 120 minus 80 is 40. And then 40 times 2 is 80, and the feet cancel, so we'd have 80 pounds of rope. That force would be 80 pounds if y was equal to 80, and so on. So this 2 pounds per foot times this 120 minus y, this distance in feet, represents the force that is being exerted by the weight of the rope. And so this is my force function. Again, it's not constant. It's dependent upon the height. So every time I pull up a little bit of rope, now there's not quite as much weight that's pulling it down, right? So the force is decreasing over time. So this is going to be our force function. And I'm going to go ahead and remove the units there. So we know that the feet units cancel, so the force that we're talking about is in pounds, which makes sense because force has to be pounds if the measurement of distance is in feet. And so to clean it up a bit, we are essentially integrating from 70 to 120, and then we have 2 times 120 is 240 minus 2y dy. If I distribute the 2 in. And then now we're just taking the antiderivative of each piece. So we have 240y minus 2y squared over 2. The 2's would cancel, so just y squared, evaluated from 70 to 120. If we plug in the 120 first, so 240 times 120 minus 120 squared, and then all of that minus 240 times 70 minus 70 squared. That's going to give us a really nice number. it's exactly 2,500. And the units there would be foot-pounds. So our unit of force was in pounds and our distance was in feet, so we have units of foot-pounds. So here it took a little bit of effort and we sort of needed to think about this rope almost in slices, right? So we're thinking about the force that is applied, how it's changing as I lift the rope up, the force is decreasing by 2 pounds each foot. And so this ends up being a linear equation with a slope of 2, and it's a negative slope because that weight is decreasing over time. Now there is a part B to this question. We're asked to calculate how much work is required to pull up the second half of the rope. So the force function is going to be the same as part A. The difference here is going to be the limits of integration. So we're still integrating that force function of 240 minus 2y. That's the version after the 2 has been distributed. But now what we have to do is think about what are those limits of integration going to be? Y equals what to y equals what? So how much work is required to pull up the second half of the rope? So here, half of the rope is 25 feet. So we have y equals 70 as the bottom of the rope and y equals 120 as the top of the rope. So halfway is going to be y equals 95. So that's 25 units away from 70 and 120. So the question is, are we going to integrate from 70 to 95 or from 95 to 120? What's going to give us the right value for how much work is required to pull up the second half of the rope? So the correct answer is from 95 to 120. So we are going to make our limits of integration go from 95 feet to 120 feet. And let's sort of talk about that. So the first problem, part A, we started at y equals 70. And we sort of talked out that specific value y equals 70 and the force right there. At y equals 70, when we plugged in that value, we said, well, the whole 50 feet is hanging there at 2 pounds per foot. That's 100 feet of force that's being exerted at that time. And then we said what happened at y equals 80. Well, 10 pounds had already been lifted at that point. So there was 40 pounds left, or excuse me, 40 feet left. And so there's 80 pounds of force still left to exert. So we're still working on that no pun intended. We're still continuing to pull up the first half of the rope from 70 to 95. So more force is being exerted at that time because there's more weight to the rope at that time. So we need to integrate from 95 to 120. Now this sort of maybe stumps people a little bit because they're maybe putting themselves on the top of the building and thinking about, well, the first half of the rope is this part right here on top, like the top of the rope. That's the part that's literally going to hit the top of the building first. So that's the first part of the rope. So I understand the confusion, but in terms of our calculation, the first part of the rope's force is between 70 and 95. And then the second half of the rope's force is exerted between 95 and 120. And so let's do this computation and finish this out. So we have 240y, we already integrated this, minus y squared, evaluated from 95 to 120. And I'm just going to give you this value because it's very similar to the previous one in terms of just putting in 120 into both and 95 into both. We get 625 foot-pounds. And we want to think about sort of the reasonableness of this answer and why it makes sense that we did do the right one. So we said the total work required to pull up the rope to the top from part A was 2,500. And so you have to imagine that the first half of the rope would require more work, more energy to be exerted because there's way more force, there was way more weight that's pulling it down initially, versus the second half of the rope should be easier to pull up. I've already got half of it up. So this value being 625 feet, being, far less than half of 2,500 makes sense because it's, I've already done sort of the hardest part in pulling initially, right? That first 25 feet up would take a lot more energy, a lot more work to do than the second half. There's one final thing I want to mention, not to confuse you, but to sort of give you a different option. I elected to think about this problem where the building was the y-axis and then ground level was the x-axis. And that's what made my limits of integration 70 feet to 120 feet. That's where the rope exists in my diagram. But we could have done something different. We could have elected to make the bottom of the rope the x-axis. So I could have chosen to make the bottom of the rope the x-axis, therefore making part A, the setup of part A, the integral from y equals 0 to y equals 50, instead of y equals 70 to y equals 120. However, that is also going to change your force function as well. It's still going to be 2 pounds per foot, but now that arbitrary distance traveled isn't going to be 120 minus y, it's just going to be 50 minus y dy. And that does give you the same answer, that 2,500 foot-pounds. And so that makes the setup for part B, if we would have chosen the x-axis to be the bottom of the rope, y equals 25 to y equals 50. Again, of that 2 times the quantity 50 minus y dy. So that's just an alternative way that we could have set this up and still arrived at the same numerical answers. It's just deciding where to put your x-axis, and then that will then change the y values. But no matter what, we're always going to integrate over where the rope exists, right? Over where we're even potentially doing any work. So if our x-axis is the ground level, then we don't start doing any work until the y value of 70. But if we make the x-axis the bottom of the rope, then we start doing work immediately because the bottom of the rope is now y equals 0. So that's an alternate way to think about it if it helps. Let's look at another rope example. A 5-pound bucket is lifted from the ground into the air by pulling in 20 feet of rope at a constant speed. The rope weighs 0.08 pounds per foot. How much work was spent lifting the bucket and rope? Let's start by drawing a diagram. So here I've constructed a rope, which is this thin rectangle, and at the bottom of the rope there's a 5-pound weight, which represents the bucket, and the length was 20 feet again, and I've made it so that the length lies along what I'm calling my y-axis, so the rope extends from y equals 0 to y equals 20, and the bucket, the bottom of the rope, is right along the x-axis. So the integral that I'm setting up to find the work spent is going to be from y equals 0 to y equals 20. But to find the force function, the force is essentially the weight. So my force function f of y, just like last time, essentially represents the weight, which is changing as the rope gets pulled in. So imagine that the top of this rope here is maybe being wound around a wheel of some kind, like a winch, and it's being pulled up or being pulled in. So the total weight, well, 5 pounds is always hanging at the bottom from it, so that part is a constant, plus the remaining weight is the part that is varying over time. So each foot of this rope weighs 0.08 pounds. So we're looking at 0.08 times, in this case, 20 minus y, where y is some height between y equals 0 and y equals 20. So if I think about this just at y equals 0, so sort of initially, does this truly give me the weight of the entire rope and the bucket? Well, if I plug in y equals 0, then I end up in the parentheses 20 minus 0, which is 20, and 20 times 0.08, that's going to be the weight of the rope, so that's going to be 1.6 pounds, and then plus there's always 5 pounds at the bottom. So yes, this does make sense. And then let's actually just talk about what happens at the end. So at the end, at y equals 20, 20 minus 20 is 0. And that's because I pulled in the entire rope, so there's no more rope to pull in, just the weight that's hanging there, that 5 pounds. And so of course this is going to vary, right? We're considering this integral, these infinitely thin slices. So this is going to vary from y equals 0 all the way up to 20. So this is my function of y. This is my varying force. And again, that force is a weight. Just like the previous example, the weight of the rope, it's decreasing over time as I'm pulling in the rope. So now here it's just a matter of doing this integration. So the integral from 0 to 20 of 5 plus 1.6, 0.08 times 20 minus 0.08y, so I can distribute that in first. Then I can gather my like terms. So the integral from 0 to 20 of 6.6 minus 0.08y, I missed a 0 up here, 0.08y dy. So the antiderivative is 6.6y minus 0.08y squared over 2. If I divide by 2, I get 0.04y squared from 0 to 20. And then if I plug in 20, 6.6 times 20 minus 0.04 times 20 squared, and then I'm supposed to subtract plugging in 0, but that's just going to zero out all my terms on this one. So I end up with 116 foot-pounds. In this example, the units worked out perfectly. My weight or my force was in pounds, and my units of distance was in feet, so my overall answer is in foot-pounds. Now let's talk about another work problem where we're going to be pumping liquid from a container. Pumping a liquid out of the top of a tank requires work because the liquid is moving against gravity. To calculate this, we imagine the work required to lift small disks of liquid up and out of the tank. So we're imagining cross sections. So we're lifting a series of masses against gravity and allowing the liquid to spill out once the top is reached. So over here what I have is a two-dimensional image of what's meant to be a three-dimensional cone. So imagine you have like a sugar ice cream cone and you have some melted ice cream in it. So that's a liquid. And the melted ice cream is maybe 2/3 of the way in the cone. And you're interested in pumping that liquid out of the top of that cone. So for these examples, we're usually pumping water out of a tank. And so this requires work. We are lifting these disks against gravity to allow them to spill out of the top. And what's going to vary in these systems is the volume of each disk and the distance each disk needs to be lifted, measured by taking the total height and subtracting the present height of the remaining liquid y. So in our ice cream cone example, let's kind of imagine taking a disk of that ice cream that is, let's say, a height y from the very bottom of that cone. And so we're thinking about raising that one disc of liquid up out of the top of the ice cream cone. So how far would that disc have to travel? How far up? Well, we have to know the total height of the ice cream cone. And then what we're going to have to do is subtract the height of that disc. So let's say that particular disc is at a height of 4 feet. And the total height of the cone is 10 feet, gigantic ice cream cone apparently. So how far does that disc have to travel? Well, if it's at a height of 4 feet and it's got to get up and over the height of 10 feet, it has to travel 6 feet. So it's the height, the overall height of the cone, or essentially the top of the tank, minus that particular disc, which is at a generic height of y. So in general, for emptying a tank, the formula to find the work is the integral from y equals a to y equals b of f of y dy. But that's really generic, so we're going to get a little bit more specific here. The work, y equals a to y equals b, well, what are a and b? So y equals a to y equals b is representing where liquid is even present. So that's the only part we are going to integrate on. We're going to do work on any liquid. So in our example of the ice cream cone, y equals a to y equals b is going to extend from the very bottom, the tip of the cone, up to wherever that height of the melted ice cream is. So that's y equals a to y equals b. Distance lifted, we already talked about the idea of lifting that one slice of the liquid, is going to be found by doing the overall height of the tank minus y. So that's going to be the overall height of the tank minus generic y, because we're taking all of these different slices at heights y between a and b. And then the part that we're going to have to work for, essentially, is finding the increment of force times dy. And so the increment of force is broken down to be the weight of the liquid. So it really depends on what liquid we are trying to lift. So they have different densities, liquids. So think about water versus ice cream. So they have different densities, so that's going to have to be taken into account, the weight of the liquid, and then the volume of the slice. So just depending on what the cross-section looks like. What's the shape of that cross-section? Let's jump into an example. A circular swimming pool has a diameter of 24 meters, the sides are 5 meters high, and the depth of the water is 4 meters. How much work is required to pump all of the water out over the side? Note, the density of water is 1,000 kilograms per meters cubed. We'll start by sketching a diagram. Alright, so here I have a right circular cylinder. I have the diameter is 24 meters, the height is 5 meters, and then the height of the water is only 4 meters. So the water doesn't go all the way to the top. So let's go ahead and start to set up our integral to calculate work. So work is going to be the integral from y equals, in this case, if I think about the x-axis as the bottom of the pool, then that means my limits of integration are going to extend from y equals 0 to y equals 4. We only integrate over where the liquid is present. So again, if the bottom of the pool is the x-axis, that's y equals 0. The depth of the water is 4 meters, so that means that the limits of integration extend from 0 to 4. And then what we're integrating, that force, f of y, has those three components. So we have distance lifted times the weight of the liquid times the volume of the slice. Alright, well let's go ahead and draw a representative slice. So when we think about a slice or a cross-section, we're talking about essentially sort of a circle, and that's not a very good circle, but it'll do. And it's at a generic height of y from the x-axis, being the bottom of the pool. So what's the distance lifted by a generic slice? Well, it's always going to be the height of the tank. So what's the highest point that the water needs to overflow over? So that's going to be 5 minus y. So the distance lifted is going to be the quantity in parentheses, 5 minus y. And let's go ahead and attach some units there for a second. That distance is going to be in meters. And then we have to calculate the weight of the liquid. And so that's why this note is given here, the density of water. So because we are given the density of water is 1,000 kilograms per meters cubed, I'm also going to have to include gravity to that to find the weight. So it's that difference between the fact that pounds already includes weight, but if we're given grams or kilograms, or we're working in the metric system, we have to multiply by acceleration, which is gravity. So this applies when, again, when grams, kilograms, we're going to need to take into account gravity as 9.8 meters per second squared. So the weight of the liquid is going to be the density of the water, which is 1,000 kilograms per meters cubed. So I'm going to go ahead and put in 1,000. And below it, I'm going to put the units. So that's kilograms per meters cubed. And again, we have to include gravity here. So 9.8, and that's meters per second squared. And then finally, what we need is the volume of the slice, dy. So dy is that thickness of the slice, essentially, and we know that because we're doing an integral, the thickness of the slice, so dy is this little thickness here, the thickness of the slice gets infinitely thin because we're computing an integral. So the volume of the slice, well, the slice is essentially a circle, right? It's just a circle, and the cross-section area, essentially, if we make it infinitely thin, is not varying. So across this whole tank, the cross sections are always going to be a circle with the same area each time. So here it's kind of a nice volume of a slice formula. So we have, if I think, I'm going to pull out that individual cross section for a second. So let's think about just this like individual cross section. The height is dy, and then the circle for the area of like the base there, so that area is pi times the radius squared. Well, the radius is going to be 12 because the diameter is 24. So the radius is 12 meters. So my area is 144 pi meters squared. So the that's the area of the base, and then the height is dy. So that's what we're talking about, like the volume of the slice. So we need the cross-sectional area and then times dy. But again, that dy is the differential, so it's getting infinitely thin as we integrate over 0 to 4. So the volume of the slice dy is constant. It's 144 pi, and then dy, that's the height. So that's base, which is the area of the circle, times the height dy. And the units of 144 pi were in meters squared. So I was trying to just kind of separate here this individual cross-section, which is its own little cylinder, and the volume of a cylinder is the area of the base, well, the base is a circle, so the area of the base times the height. So the area of the base is just a constant 144 pi, and then the units there was meters squared. All right, now that that cross-section is out of the way, let's talk about the units and make sure everything checks out there. I have meters and meters squared on the top, that's meters cubed, and a meters cubed on the bottom. So that means those are going to cancel out. Meters squared is going to cancel with the meters cubed on the bottom. So the units that I have remaining for this entire big quantity inside here of the force is kilograms times meters per second squared. which is exactly newtons, and that is the unit of force here in the metric system, which is what we're using right now when we're talking about these units of measure, meters and so on. So this checks out. If we were talking about feet and pounds, we would need this all to work out to be pounds, but here it works out because the force is in newtons. And then y equals 0 to y equals 4 is in meters, so when we compute this integral, we will get out Newton meters, which are joules. So now the units are just a great check to make sure that you have included all of the different pieces that you need, but then we can sort of drop the units when we now go to integrate. And we can pull out all of these values, 1000 times 9.8 times 144 pi, all of those are just a coefficient. So it's just a number that's multiplied times 5 minus y. So I can pull it out of the integral completely to make my integration simpler. And if I multiply it all together and I pull it out to the front, it's going to be a really big number. And I'm going to go ahead and tell you that number is 1,411,200 pi. And then the integral from 0 to 4 of 5 minus y dy. So don't multiply the pi in. You can go ahead and leave it in terms of pi, this coefficient in the front. And now all we're integrating is 5 minus y. So that's going to be 5y minus y squared over 2, evaluated from 0 to 4. And of course, all of that is times that 1,411,200 pi. And so we'd of course plug in the 4 into each y. So we have 5 times 4 minus 4 squared over 2. Thankfully, plugging in 0 is not going to do anything there. And if we multiply all of this out, here's what we get: 16,934,400 pi, of course, we're going to leave it in terms of pi, joules, or Newton meters. Either one is fine. So it is primarily the setup of these problems that tends to be tricky, but it's helpful to think about that these three pieces are required: the distance lifted, the weight of the liquid, and then the volume of the slice dy is going to be probably the hardest part. This one was an easy example because the slice was a constant sort of volume each time, right? So that area was just always, it didn't matter where we were between 0 and 4, that cross-section just had an area of that 144 pi. But we'll see examples where that cross-section varies. Alright, there is kind of a little bonus question, an add-on question to the previous example. What if the tank had a lid and a 2-meter spout added to the top? How would this affect the setup? So now this water that's being pumped out of the tank has to get up and out of this 2-meter spout. So here's the nice thing. Not much would change. So our work formula would still be the integral from y equals 0 to y equals 4. So we're still just integrating over where the liquid is present. What's actually going to change here is the distance traveled. So our cross section, which was at a height of y, now it has higher to travel. So now it has to get up and out of this 2-meter extension and travel a total of 7 meters. So the difference is that our distance traveled is going to be 7 minus y. But other than that, everything else is the same. We're still going to have that 1,000 times 9.8 for gravity, and then that cross section, which was 144 pi. Pi times 144 is the same thing, dy. So the only thing that is going to change on this problem is the height that that cross section has to travel, the distance that it has to travel. And now in this example, we have a right circular conical tank of altitude, which means height, 20 feet, and base radius 5 feet, has its vertex at ground level and axis vertical. So we essentially have that sort of ice cream cone situation I was talking about earlier. If the tank is completely full of water, find the work done in pumping all the water over the top of the tank. Note the weight density of water is 62.5 pounds per feet cubed. So this problem we are now dealing with feet and pounds, so that's just something to sort of keep in mind. And so we have a diagram started here, so I have sort of this triangle that's like the two-dimensional representation of the three-dimensional cone, and we'll label it with the values that we were told. So the height of this tank is 20 feet, the radius is 5 feet, and we'll say that the slice is at a height of y. And then we'll pretty much get started on setting up the integral. So to calculate the work, we're doing the integral from y equals 0. So the water starts at the ground level, which we're going to assume is the x-axis, so that's y equals 0. And since the tank is full of water, the limits of integration are going to be from y equals 0 to y equals 20. And then we have those three parts that we need to fill in. So we need the distance lifted, and so we're focusing on a slice. So the distance lifted of this slice, which is at height y, is going to be the total height of the tank, which is 20 feet, minus y. So we're going to have 20 minus y. And then what we're going to need is the weight of the liquid. Well, the good news is that because we are given weight density in terms of pounds, we don't need to additionally include gravity. So our weight of the liquid is simply 62.5 pounds per feet cubed. So I'm going to put 62.5, and let's put the units on there just like last time, pounds per feet cubed. 20 minus y, that was in feet. And then what we're going to need this time is the volume of the slice. But the volume of the slice isn't constant anymore. So it definitely depends on the y that you choose. So if I were to choose a smaller y value than the one that's constructed here that's more towards the top, if I were to take a slice more towards the bottom, that volume would be less. That would be a lesser amount of volume than towards the top, because of how a cone starts really narrow at the bottom and then widens towards the top. As opposed to that previous example, each circle was the same area, so when we had that height dy, so each volume, each disk was the same as I stack them up vertically. But here, these disks, although they are still little cylinders, the radius of each cylinder is different. So let's sort of take out one of those cylinders and sketch it and sort of think about that for a second. So if I take out sort of one of those individual little cylinders here, the volume of that cylinder is pi, and then we're going to need r squared h, right? But h is dy. Dy is that little height. So pi r squared dy. It's just that this time, what's r? So r is not a fixed value like it was on the previous example, where r was just that fixed radius every single time. R is going to vary, and it's going to vary as a function of y. I need to essentially find r by doing right minus left. So thinking about sort of the right side of this cone as a linear function, and then thinking about doing that linear function right minus left, but left is just the y-axis here, so that's just minus 0. So let's think about what the equation of this line would be. Well, the line is passing through the origin, if I think about this as the y-axis straight down the middle, and so I'm really just in need of the slope to write this line in slope-intercept form, right? Y equals m times x. Well, what's the slope? I'm going up 20 units from the origin, that's the height of the cone, and I'm going over 5 units. So up 20 over 5, 20 over 5 is 4. So this is y equals 4x as a linear function. So that's the equation of this line as a function of x, but I need everything to be in terms of y. So I need to do right minus left here. So instead of thinking about this as y equals 4x, I have to think about it as y over 4 is equal to x. Divide both sides by 4. So this radius here is y over 4 minus 0. That's going to be this radius as I travel from y equals 0 to y equals 20. It's getting bigger each time. So that's what's going to go inside here. Again, when I think about sort of the volume of the slice was a little cylinder. The area of a cylinder is pi times the radius squared. The radius was not constant. The radius is varying. So I need to replace that with y over 4, technically minus 0, right minus left, squared dy. So I'll fill in over here, r was y over 4. All right, so that's what's going to come over here as the volume of the slice. So we have pi times, let me go ahead and start to simplify this a little bit. Pi over 16, 4 squared is 16, and then y squared dy. And the units of pi over 16 y squared is going to be feet squared. So dy is that height, right? So this part right here, pi times y over 4 squared, that's just the area of the base, which is the area of a circle, times dy. So this portion right here, pi over 16 y squared, has units that are feet squared. So what's going to cancel in terms of units? Feet and feet squared will cancel with the feet cubed on the bottom, leaving us strictly with pounds. And that's what we want to happen. We want to be integrating a force, and pounds is a force. Now this time, the only thing we can pull to the front is 62.5 pi over 16. So that's the coefficient, but y squared is a variable. I cannot pull that out. So in terms of actually integrating this, I can take out the 62.5 pi over 16, and then the integral from 0 to 20, and then the y squared times 20 minus y. The best way to integrate that would be to distribute the y squared. So we're going to have 20y squared minus y cubed dy, the differential, and 62.5 pi over 16 times the antiderivative here is going to be 20y cubed over 3 minus y to the 4th over 4, and that's evaluated from 0 to 20. And of course we're going to plug in 20 into both of those y's. Plugging in 0 is going to just make those terms go away, and so the overall answer here ends up being, here I did go ahead and multiply in the pi to arrive at 163,624.624, and then we would have foot-pounds as our units. And these problems would definitely require a calculator if actually evaluating, but not if you're just setting up, because the real ugly numbers come with the evaluation of the definite integral.